Swayam Prabha. Digital India. Educated India.
Hello and welcome to a very new topic today on torsion. Until now, what we have covered in this course, if you remember the last topic, we were looking at members which are essentially loaded in the axial direction. For example, if I have a member like this, say a circular tube or maybe a solid tube or a rectangular tube, we were essentially pulling it or pushing it, so essentially applying the forces along the axial direction. What we are going to see in this particular topic of torsion is a completely different kind of loading. So instead of pulling it or pushing it, I am going to try to twist it. So as you can tell, this loading, this twisting loading, as my hands move like I'm applying the torque, is very different compared to pulling or pushing this particular bar. So you might be imagining that the kind of effects these torques induce on structures are completely different than what the axial loadings impose. They are different, but there are several analogical similarities that will help you sort of correlate the structural behavior under torsion with the structural behavior under axial loading. Now, before we jump into the topic, I just want to make you aware that torsion, it exists in our life in n number of ways which you are probably not even aware of, or you're aware of, but you keep doing your daily activities without properly recognizing that where or how you're applying the torsion forces. Some of the examples we have discussed before in the introductory lecture. For example, when you are opening this bottle of water or you're tightening this bottle of water, you're essentially applying a torque. So if you observe both of my fingers, what I'm doing is that at this end I'm applying this force here, and at this end I'm applying this force here. So I am essentially applying equal and opposite forces to tighten this one, which comprises of a torque. If you are following the right hand rule, this torque is pointing towards this axis of this bottle that is there. Another classic example, whenever say you wake up early in the morning, you go to the washroom, you open the tap of water, right? Now, unless of course you have one of those fancy taps, and I'm sure you have seen these kinds of taps I'm talking about on campus, which have those the member horizontal member on top of the tap, which you sort of have to twist, right? So these are some of the very common examples of torsion which are there in our daily life. So along with these ones, let's look at some of the other common examples of torsion that we may have, right? So one of them is the screwdriver. Remember, we had talked about this one as well. Suppose when you're tightening a screw, that the type of the nature of the force or the nature of the moment that you're applying essentially is a torque along, of course, this particular axis of the screwdriver that is there. When you are washing clothes, or when you are wringing the clothes, when you're wringing the water from the wet clothes that are there, you're essentially applying also a torsion. This is the type of tap that I was talking to you about, the non-fancy one, where you still have this horizontal member, and to close or open the tap, you're applying the P and P on both the sides, over here as well as over here. Now opening a bottle of water, as I showed, or mechanisms within cars, the gears, the shafts, the axles, they all undergo this kind of torque or torsion forces over here. Now since we have to represent engineering systems in terms of diagrams which we comprehend, this is a type of a beam that you're seeing, or a circular shaft, right, where you're applying a force P on the top over here and the P at the bottom over here. On this, you have attached a vertical member of this one, and then you are applying a force P and P. And if you try to gauge the effect that this P1 and this P1, equal forces separated by a distance. So as you can imagine very well, here your torque is going to be what? Here your torque is going to be, and torque is typically represented by this variable t over here. So for this one, your torque is going to be P1 times D1, right? And for this one, the torque is going to be your, so if I call the previous one as T1, so if I call this maybe T2, T2 will be equals to P2 times D2 over here, right? And if you appreciate the differences what we discussed earlier compared to the bending moment, right? Now the torque acts essentially along the axis of the member. So here if you take P1 and P2 and if you sort of curl your fingers, your thumb points towards the axis of the member, either inside or outside. For example, for the P2, if you go from this P2 to this P2 over here by curling your fingers again, your thumb points outwards from this particular axis that is there, right? This page shows the same circular shaft along with the torques which we just wrote in the previous page, P1 D1 and P2 D2, and these are the representations of the torques. So torques are typically represented using these double arrows, right, or using these curved arrows which are there, and with these double arrows, or if you follow the direction of the arrow, and as indicated here, that if your fingers are curling along the direction of the moment, then your thumb points about the direction of the torsion vector. So you can tell from here as well, this P1 and P1, if you're going from P1 to this P1, if you just curl your fingers, you will see in this case your torque T1 points towards the axis of the member and towards the longitudinal axis, and your torque T2 points away from the longitudinal axis. So this is a very standard representation of the torque and quite convenient to draw as well compared to these round arrows which are here, right? So now just moving ahead, how do these structures behave under torsion? Now this is extremely important to understand the behavior of shafts which have different types of cross section, and for our basic course on solid mechanics, we are mostly going to look at circular bars or bars which are having circular cross section, and there is a reason for that. Now when you look at these circular bars which are there, as you see in this particular figure as well, right? So when you have these circular bars, and if you are drawing crisscross lines, as you have these going along the circumference, and these are lines which are along the particular axis of the shaft that is there, if you take a look at any of these points or two sets of points, and for this circular bar, when you are applying the torque, right, what you will essentially see, for example, if this circular I'm applying the torque, and suppose this moves, suppose this had these horizontal grids and the circumferential grids all around, when you will see a set of 2 points which are there, they all move about that same circumference they were a part of before you had applied the torque. What I mean by that is, suppose you are looking at these 2 points, suppose I call this point as A and I call maybe another point here as A prime. After you have applied the torque, what has happened to A is that A has simply maybe moved to another point over here. So this is my new position of A, and A prime has moved to another point over here. So this has my new A prime, right? But remember, as you can see from the figure as well, they were a part of a circumferential line, which was this circumferential line which we were looking at, right? And after you have applied the torque, they have simply shifted along the same circumferential line. So essentially they have not moved along that horizontal line. They are on the same horizontal lines. A is along the same horizontal line, A dash was along the same horizontal line, and this horizontal line, instead of being horizontal, has simply twisted. So they are moving along the same circumference. So this red circumference which we just drew over here, this is essentially the same circumference that is over here, only that the points have shifted. Right? Now to understand this further, let's look at a short video where you will see that when you are applying the torque, how these points move along the same circumferential line. What you will see in this video is that when the torque is applied on this circular shaft that is there, the points which are on a particular cross section continue to remain on the same cross section. So this shows the geometric lines of the shaft, and now you are going to go and apply a torque at the very end. And once you apply it, you see there is no contraction or elongation of the member, and the points have simply shifted along the same cross section. So if we have to take a static snapshot of the video that we just saw, and from this figure which we just deciphered, if I have a horizontal line like this, A to B over here, after I'm applying this particular torque T, now here this particular side is clamped, so if you're applying this torque T, what you will develop is an equal and opposite torque at the support as a support reaction at this particular end B over here, right? Now when I'm applying this torque T, and as we just discussed, that these points just move along the same circumferential line that you have, this point A now moves to a new point A prime over here. So what was my A? This point A over here, right? It moves to a new point which is A prime at the top, right, along the same circumferential line, and as a result of which it inscribes an angle, right? This particular angle, this phi that you see over here, it is known as the angle of twist. So let's just write that down, and we will see that we will deal with this angle of twist through and through. So this is known as the angle of twist, which makes sense why it's called twist, because when you're applying a torque, what you're essentially doing, you are twisting the different ends, right? Now a key difference between circular members and non-circular members, and why on a basic course of solid mechanics we study circular members, right? This is what we just saw, that points on the circumference move along the same circumference. But if you are looking at a rectangular member or a member which is a non-circular cross section and a completely solid member, when you're applying the torque, the torsion force, you will see there is a particular phenomena which happens. For example, if you see here, you see these points that you can see over here. Initially, these points were maybe along the same. If I take a perpendicular cross section about this longitudinal axis of this shaft, which has a rectangular cross section, if initially they were on the same perpendicular axis to this longitudinal axis, after I'm applying this torque, after I'm applying this torsion over here, let's see what happens to those points. Those points sort of do not remain on the same perpendicular axis, they undergo some kind of a shifting. So this point over here has moved slightly to the right, and the bottom point has moved slightly to the left, right? Now do you know what this particular phenomena is called? Maybe some of you know this already. This particular phenomena is called warping, right? So what is warping? So let's just write that down, right? Warping essentially means that the cross sections which were perpendicular to the longitudinal axis, after you have applied the force or the moment or the torque in this particular case, that cross section is no longer perpendicular to the longitudinal axis. It undergoes some kind of deformation. Some points have moved to the right, some points have moved to the left, and this leads to the phenomena of warping. Now the phenomena of warping and how it is associated with the torque you will learn probably later in an advanced solid mechanics course. What we are going to focus in this particular course are members which do not undergo warping, which we just saw in this case, that for the circular cross section where each cross section is still perpendicular to the longitudinal axis, and the points on the cross section when you're applying the torque simply moves up or down depending upon the nature of the torque. So in this case we have no warping. This is extremely important. If you have warping, there's a whole set of different formulas for calculating this particular guy phi over here. Remember the angle of twist which we marked in the previous page, right? Now, so again, just reinforcing that idea, this case is the case where you have no warping is known as pure torsion. So this is pure torsion, means when you have no warping, that is the cross sections still remain perpendicular to the longitudinal axis, and as indicated here, the points on the circular cross section remains on the same cross section, and you do not have any phenomena of warping over here. Now I want to draw your attention to again how these points are moving. As I said, the points on the cross section remain on the same cross section which are there. So if in this circular member, if say I take these concentric circles, right? So suppose here is my central point. So this is my central point over here, and say I've applied the torque, and whatever was my point A has moved to A prime, another point B has moved to B prime, and so on. Now if you take these concentric circles which are sort of emanating from the center, the core, all the way to the outside, right? Now if I just have to join them, say using a particular line over here, suppose this was my original configuration, and after I've applied the torque, I am drawing an exaggerated figure, these points have moved to the top over here, right? So suppose this particular point here was my A, A has moved to A prime, right? Internally, another point, let me pick this point over here. Suppose this point was B, this point B has moved to B prime, right? Now, can you tell that what is the difference in this movement or difference in the nature of the movement? The circumferential points moves more, right? A has moved all the way to A prime, and as you're approaching towards the core of your towards the centroid of your circular shaft over here, for example, if you take a point exactly at the center of the core, that point does not move anywhere. This particular point here, let me call this C as the center, that point does not move anywhere. So as you are moving further and further away from the center, you are going to have higher and higher amount of displacements, but again along the same circumferential line. You are not having any warping, the points are not moving to the left or right, it is simply shifting to the top or to the below over here. And the displacement of these points keeps on reducing as you are approaching from that outside periphery to the inside point over here, right? So let me poke your memory slightly, or poke your knowledge of stresses and strains right at this point pertaining to this topic of torsion. So if we just go ahead, right, again, if I take 2 points, or if I take a particular element instead of taking points, let me go ahead and on the surface of this circular shaft over here, let me draw a particular element. So if I have, say, if I take this particular element that is there, right, what has happened to this element after I've applied this torque over here? This element has simply kind of changed its shape. This element has somehow become like this over here, right? Now, as is mentioned here as well, that elements undergo a change in shape and only a very minor contraction or elongation, that is very negligible changes, very negligible shifting of the points about the axis, about the longitudinal axis, but you have a more appreciable shifting about, you know, about these particular axis, and very minor shifting about the longitudinal axis, right? Now, from what we have learned until now, do you remember what kinds of elements or what kind of stresses in an element causes these kinds of shiftings? Remember, the elements where you are simply applying a force on the sides and it just undergoes a change in shape without undergoing expansion or contraction. Yes, you have guessed it right. These are the elements which are in pure shear. When you have an element and if you're applying an expansion or a contraction, the element expands or contracts, right? Whereas if you're applying shear, then that particular element only undergoes a change in shape. Exactly what is going on here. This element, this red colored element which we just drew over here, this is not undergoing any appreciable expansion or contraction, but it is undergoing a change of shape. So that leads us to a very, very important conclusion, that when you are looking at elements on the surface, or you will see that on the insides as well, wherever you look at, and if you take these elements which are perpendicular to the longitudinal axis, see this element which we drew, we essentially connected 2 points on 2 different circumferences which were over here, right? 4 points essentially to draw this element, and these circumferential sections, remember, are still perpendicular to the longitudinal axis. If you take those elements, all these elements are in a state of pure shear. So all elements, that is, this is a very important conclusion about torsion. So all elements are in a state of pure shear. This will make life much simpler, and you will see a lot of the derivations are hinged, are based on this particular assumption, which is quite a realistic assumption when we are talking about circular shafts which are in pure torsion. Next, what we are going to do, we are going to look at how to utilize this condition that all the elements are in pure shear and derive certain relationships for since they are in pure shear, automatically your mind starts to think we are going to talk about shear stresses, I'm going to talk about shear strains. Also, how are they related with that phi that is there, that is the angle of twist. Next, what we are going to derive are some of the very fundamental relationships on the topic of torsion. These relationships will help you to solve problems, the textbook problems on torsion, as well as deal with problems in real life structures which are undergoing the phenomena of torsion. Now let us begin maybe where we left off. Where we left off, if you remember, we were looking at a solid circular shaft which was having torsion at both the ends, and what we saw that each of these elements which we were drawing on the outside of the surface, they were undergoing amount of shear deformation, right? So they were simply having a change of shape without any appreciable expansion or contraction. Also, one thing which we looked at, that this shifting of the elements, shifting of the points about the same circumference of the circle, it happens maximum at the outer surface, and as you approach towards the centroid, as you approach towards the core of this circular shaft, it keeps on diminishing. So what does that tell you? That tells you that the amount of shear, amount of movement relative to one circumference to the other, the points moving up and down, this movement happens more predominantly on the outer surfaces than on the inner side, than on the inner lines which we were looking at. So that also brings you to the conclusion that the shear stresses and the corresponding shear strains are going to be highest for the elements which are located on the outer surface, and it is going to slowly going to reduce, slowly going to decrease to almost zero or negligible amount of stresses as we approach towards the centroid. So with that fundamental understanding, let's dive in and try to derive some of the expressions for the shear strains, and the most famous torsion formula. So again, where we just going to where we left off over here, what we are looking at, again, the circular shaft that we had seen before. And in this circular shaft, if you see, this was on horizontal line which was there previously. After you have applied a particular torque, let me indicate the torque over here. So I have applied a torque like this, T. So the points are moving relatively up. This point which was over here at this particular point has moved over here, right, and has inscribed an angle. So this phi, remember, this phi still remains as your angle of twist. So let me just write that down. This phi over here is still my angle of twist, right? And as we just discussed, that this shifting is going to happen maximum for the points which are on the periphery, and it is going to go zero as we approach the centroid or the core, and intermediate, you will have intermediate levels of shifting compared to the maximum shifting at the exterior point and the minimum shifting at the interior point, right? So here, if I have to sort of take this line which was initially horizontal, and after you have applied the torque, it has somehow become like this over here. So this particular angle that I have, this angle is going to be my gamma max, right? This is the maximum amount of shear which has happened on the periphery. Now, as you are going inside, if you take an intermediate section which is not at the extreme periphery and not at that central line that is there, for example here, if you take a look at an intermediate element, this was the element which was there before you applied the torque. Now after you have applied the torque over here, let me mark the torque again. If you have applied that particular torque, T, what has happened, this rectangular element has now undergone a change of shape, again without any appreciable elongation or contraction, right? So if this was the gamma max which was happening at that exterior surface, at an interior surface it is going to be a slightly lesser angle. Let's call this gamma. So what we are seeing, that when you are having this angle due to this torque gamma, the point A which was over here now has moved to a new point A prime, right? So if I apply the torque in this direction, this point has moved up, it has gone to A prime, as a consequence of which you have inscribed this phi. Now remember, whether you are looking at the point on the outside or if you are looking at the points on the inside, this phi remains the same. Phi is just the angle of twist. It is just the points on the outside move more relative to the points on the inside that is there, right? Now coming back to this one again, if we have to write some of the formulations which are there, if I take this triangle which is over here, that is A B A prime, so let's just write that down. So if I take this triangle A B A prime, right? From this triangle, I can write the relationship. If I take the tangent of gamma, if I take tan of gamma, that becomes equals to A prime divided by the length. So it becomes equals to A prime divided by the length L, right? Now, for this same arc, this A prime, which it has inscribed in this in this cross section over there, if I try to relate with this inner diameter phi, remember the outer diameter here as is shown is r, and wherever on the inside I'm taking the cross section, that not diameter, the radius, the outer radius is r, and the inner radius at any particular where I have taken a subsection of the shaft, if I'm not on the outside, somewhere on the inside, if I call that as rho over here, for this shifting of the point from A to A prime, I can also write it as that A prime, it is going to be what? It is going to be equals to my rho times phi over here, right? Now, if you see this first equation which is there for small angles, we are in this course we are primarily dealing with small deflections and small angles. So for small angles, your tan gamma becomes equals to gamma. So this guy I can come and write it as my gamma becomes equals to A prime divided by L, right? Now, if this is my relationship 1 and this is my relationship 2, I can utilize both these relationships. Essentially, I can substitute A prime in relationship 1. I can write it as gamma equals to rho P divided by L, right? So this is a very fundamental relationship, how you relate your strain, the shear strain, with the wherever you are looking at, what is the radius of that particular section times the angle of twist which is happening divided by the entire length. Now, as you can tell directly from here that it is dependent on rho, right? So as we had predicted, at the core, at the line which is passing through the centroid, your rho is 0, so your gamma is going to be 0. So those points don't go anywhere, they stay on that line which passes the longitudinal axis which passes along the centroid, right? Whereas where does this gamma become maximum? Where rho is maximum, that is at the periphery, where you have this gamma max over here. So what we can write from here as well is that my gamma max is going to be R times phi divided by L, right? So these two are very, very fundamental relationships which we just derived, right? So now that we have this particular relationship, next what we are going to look at now, what we saw in this particular page over here is that for solid shafts you have the rho which is constantly varying from 0 at the center to R at the extremities, and intermediate you have the rho over here. Now if you are looking at, so this is the summary of what we just wrote in the previous slide in a more clean fashion. So this is the expression, which we just derived in the previous page. Remember, in the previous page, let me just go back and maybe write out this last expression as well. In the previous page, what we saw was that gamma equals to rho phi by L, gamma max equals to R phi by L. So if you use these two relationships again, and if you try to establish a relationship between gamma and gamma max, what you essentially get is your gamma equals to rho divided by, if you just divide these expressions, rho divided by R times gamma max. Right? So this is also a fundamental relationship. All of these three relationships is what is summarized in this particular slide over here. Right? Now, as I was saying, that this is for a solid core, a solid circular shaft over here. Now, in contrast, if you have a hollow core or a hollow circular shaft, you can easily think that how are the expressions are going to change. So for this one, what we are going to have,